Let's finish with the back of the worksheet where we are interpreting first derivative graphs. So number 3, now we're not looking at the original position graph anymore. We're looking at the slope graph, the derivative graph. And so let's think about what each of these y values represent. Anything above the axis represents positive slope where the graph is going to be rising. Anything on the x-axis represents where the slope is 0. Anything below the x-axis represents where we have a slope that is negative. So from this, if we can translate this onto a sine line, then it'll be easier to convert to our graph, because we can just look at the arrows here and sketch a graph a lot easier. So first thing, we identify critical points. So we look at our x values. X values will be a slope of where slope is 0. So it will be a -4, -2, and at 1. And then we look to see the behavior of the slope, or the y values. And negative means negative slope. Negative values means negative slope. Positive values means positive slope. So to the left of -4, we see the graph is below the axis, so that's negative slope. Above, so between -4 and -2, we have positive slope. Then it dips below the x-axis, so negative slope, and then it hits a slope of 0, but then it goes back down to negative. So now, based off of this, we're going to sketch the original position graph. We don't know where the y values are. We just have to sketch a graph that has this general behavior. So we want a graph that has a minimum of -4, a relative maximum at -2, and then where a point where the slope reaches 0, but it will continue to decrease in slope. So I just pick a random point here to represent my minimum. I pick a point up here to represent my relative max, and then I choose a value somewhere in between so that my graph will have a negative slope, level out, and then continue to decrease in slope. So we'll just basically follow this behavior from the slope sine line. So we want the graph that is decreasing, hits a relative minimum, increases, hits a relative maximum, decreases, levels out at 1 with a slope of 0, and then it keeps decreasing. Okay, so from here, now we can look at the how we can sketch the second derivative curve. So we're going to look at this graph to determine where the points of inflection are. Now, the points of inflection, if we're looking at the derivative graph, points of inflection is where the slope reaches its maximum or minimum steepness before it starts to before the slope becomes more gradual. So basically, the max and mins of your derivative graph will be the POIs, or where the critical points are for points of inflection. So the hills and valleys of your derivative graph represents POIs, just like how the hills and valleys of your position graph represents the critical points for your f prime graph. So there's a nice continuity, a nice pattern that you see between f prime and f double prime, and that is shown by this table here. Okay, where if we're looking at the f prime graph, the x-intercept will be the max and min of your f of x graph. And if you're looking at the hills and valleys of your f prime graph, those will be the points of inflection for the f double prime graph. And that points of inflection graph will be what you see in the original position graph. Okay, so back to our points of our second derivative graph. We see that our critical points are our max and mins, and these are going to be our points of inflection, so we put that on the sine line. Just like how increasing slope represents where f prime is positive, so the same way where f prime has a positive slope, indicates where our graph is concave up, right? Because if we think of this as the rate of change, uh, if the uh, um, if the slope is increasing, then we know that the second derivative will be positive. So basically, anywhere that our f prime is increasing represents concave up. Anywhere that our f prime has a negative slope represents concave down. Anywhere that our slope graph is increasing, again, that means concave up, and then concave down. So if we look at the slope of our derivative graphs, or the rate of change of the derivative graph, that will clue us in as to the concavity at those regions. Now, based off of that, we can now create our second derivative graph. We want our critical points to be on the x-axis of our f double prime graph. Any portion that is above the x-axis will be concave up. Any portion that's below is concave down. So we want the region between -infinity and -3, and also between -1 and 1 to be above the x-axis, and then the portion between -3 and -1 and from 1 to infinity to be below the x-axis. And we want the graph to connect all the way throughout. So the first part, to the left of -3, is concave up. We want the graph to be above the x-axis. Between -3 and -1, we want the graph to be concave down, so below the x-axis. Above, between -1 and 1, and then below to the right of 1. Now, based off of this, we can fill in the characteristics of our function, of our slope, as well as our concavity. All right, with number 4, again, we're looking at the derivative graph. So first thing we do is we pick out our critical points, -2, 1, and 3, our x-intercepts. Our x-intercepts from our f prime graph will be the max and mins of our f of x graph. So these are going to be our potential hills and valleys, relative extrema for our position graph. Okay, this portion is above the x-axis, so that represents positive slope. Positive slope between -2 and -1. Below the x-axis, so negative slope. And then to the right of 3, we see positive slope again. From here, we can transfer this onto our position graph. These are where slope is 0, but here, based off of the arrows, we see that we want a relative max at 1. We want a relative min at 3. So we want a hill at 1, we want a valley at 3, and then at -2, we want a point where the graph levels out, where the slope levels out, and it keeps increasing. So now these y values are arbitrary. We just have to pick y values that will represent the shape or the pattern of the slope. Okay, so again, we go back to our derivative graph to determine our critical points for points of inflection. So our points of inflection from our f prime graph will be the max and mins of our f double prime graph. So first thing we're looking for is the critical points. So critical points from f double prime would mean we look at the hills and valleys, the max and mins of our f prime graph. So hills and valleys, -2, 0, and at 2. So we put those on the sign line. And then we look at the slope. The slope of the f prime graph will tell us whether the graph is concave down or concave up. So this part, concave down, the slope is becoming more negative. Here, concave up, the slope is becoming more positive. Concave down, the slope is becoming more negative. And then concave up, the slope is becoming more positive. From here, we can transfer that onto our second derivative graph, critical points at -2, 0, and 2. We want this portion to be below the x-axis. We want this portion to be above, but connected back to 0. We want the graph to be below the x-axis to represent concave down, and finally to the right, concave up to represent where the graph is above the x-axis.